In this discussion, I'd like to talk about how to calculate the things that we've been looking at recently in other coordinate systems, known by some in certain physics application as a frame of reference as well. I need some information that we've already talked about. We talked about these things back in the chapter on geometry of space and vectors. We need to remember about the area of a parallelogram, which we'll do for what we're going to do in this discussion. Later, when we go up into 3 dimensions, we will need to know the corresponding fact for the volume of a parallelepiped. If I have a common point, vectors u and v emanate from that point, and I make copies of u here and a copy of v here, I form a parallelogram. The area of that parallelogram is the magnitude of u cross v. There's a corresponding fact for the volume of a parallelepiped, but for the purposes of this discussion, we won't be needing that. I want to think about coordinates, but I want to think about it differently than we have before. I can think of the x-axis as being the graph of y equals 0. I'll have another horizontal line, y equal 1, another y equal -1. Every point in the plane is on exactly one of those horizontal lines. Likewise, if you draw the graph of the equation x equals 0 in 2 dimensions, you get the y-axis. You can have x equal 1 or x equal -1. Every point is on exactly one of those lines. There's nothing stopping me from using something other than straight lines. I could draw some curve in the plane and just declare it to be alpha equals 0. Then draw some other curve in the plane and call it alpha equals 1, alpha equals -1. All I have to do is to make sure that these curves that I'm drawing don't cross each other. If that's true, then every point in the plane is going to have one of these alpha numbers to go with it. It's going to be on one of these curves. Likewise, I could draw curves in other directions. I could call this one beta equals 0, this one beta equal 1, this beta equals -1. As long as these curves don't cross each other, every point in the plane has exactly one curve to go with it, one beta coordinate, if you want to think of it that way. So I could make up a coordinate system that is not Cartesian. You could draw the 2 pictures that we had previously together. Notice that this kind of sort of looks like a Cartesian coordinate system, except the coordinate lines are not straight. Every point has an x and a y. Every point has an alpha and a beta. If I actually knew formulas that related the new coordinates to the original Cartesian coordinates, I could think of alpha as being a function of x and y. I could think of beta as being a function of x and y as well. The reason for that is alpha and beta values specify a single point, and every single point has an x coordinate and a y coordinate. The reverse is true as well. Give me a point, it has x and y coordinates. That point also has alpha and beta coordinates. If I knew the numbers for x and y and the relationship between these 2 pairs of coordinates, I could write alpha and beta as functions of x and y in terms of alpha and beta. So what we're going to do is we're going to select a point P. I'm not writing down the coordinates of that because I've got two sets of coordinates running around now. I'll have Cartesian coordinates. I'll say the coordinates of the point P in Cartesian is x0, y0. In the new coordinates, I'll say that alpha is some number alpha 0, and beta is some number beta 0. So I'm going to think of looking at a point P and points very close to it. So close that these coordinate curves look flat to me. Any halfway decent graph, if you zoom in on it enough, starts looking as though it was linear. It's only when you look at the entire picture you see that it's not. P has alpha coordinate alpha 0 and beta coordinate beta 0. I drew this picture very large because my smaller efforts weren't very good. I've got a point. It's got these new coordinates, alpha 0, beta 0. What I'm going to do is I'm going to change only one coordinate. So some other point nearby is going to have coordinates alpha 0 plus how much I changed the alpha, and I didn't change the beta at all. Also, I'll have another point here. I get to this point from the starting point by changing only the beta coordinate. I'll draw a vector from my original point to this point and call it u. I'll draw a vector from the initial point to that point and call it v. To make a parallelogram, this point will be the change in alpha, change in beta, added to alpha 0, beta 0. I want to know the area of this parallelogram. In view of what we just said a minute ago, though, on one level, this is very easy. It's the magnitude of u cross v. On the other hand, these are not Cartesian coordinates. So I don't know at this time that I can do the end minus start calculation. It turns out that you can, but what you get is not what we need. We need Cartesian components of vectors. At this time, we're not in a position to talk about vectors in other coordinate systems. So I need to know, for u, for instance, how much does x change and how much does y change? That's going to be the components of the vector. I also need to know the Cartesian components of vector v. Once I know that, I can plug it into the cross product formula and tell you the area of this thing. How am I supposed to figure this out? I'm going to think of x as being a function of alpha and beta. I'm going to think of y as being a function of alpha and beta. And I'm going to assume that the relationships between these variables is nice enough that I can call the relationship differentiable. And I can use delta x as approximately, and then I'm going to use our differentiability formula. Partial of x with respect to alpha times how much I changed the alpha, plus the rate of change of x with respect to beta times how much I changed the beta. The change in y is calculated in the same way. It's how quickly y is changing with respect to alpha times the change in alpha, plus the rate at which y is changing with respect to beta times how much I changed beta. Now, I'm drawing this as though it were in the standard plane. That's not going to cause me any trouble because the standard plane is the place where all the z coordinates are 0 anyway. So, splitting this up into chunks, for u, delta alpha is 0. So if I write down those two formulas that I just had with delta alpha being 0, I find out that delta x is, to this level of approximation, partial of x with respect to beta times delta beta, partial of y with respect to beta, delta beta, and my third component would be 0. I can factor a number, delta beta, out of that, and then having done that, go back to those two formulas we figured out, make delta beta equal to 0, and you will get this for the components of vector v. The z component is 0 again. These are ordinary Cartesian coordinate end minus start type vectors. So in three-dimensional Cartesian components, u is this, v is this. The area of the parallelogram is the magnitude of u cross v. So I need to do the usual thing here. For once, I remember to write my arrows over the basis vectors. This vector is in the xy plane. This vector is also in the xy plane. You can do the calculations if you want, but it turns out only the k component amounts to anything. So knock out the row and column that has k in it. The cross product is the determinant of this quantity times the vector of length 1 that points in the positive z direction. And at this point, we should feel slightly uneasy because we've seen that before. If you go back and look at one of the lectures, when I went a little off topic and started talking about linear algebra, we saw something like that once before, except we're calculating areas now. If you write out the determinant, you'll just get this. I have to take the absolute value of it in case it's negative. If we assume that our delta alpha and delta beta are positive, I don't have to take absolute values of those. This is the area of that little parallelogram that we were talking about. Now, there are various notations for this. Many textbooks use this notation for this quantity. This is a horrifically bad piece of notation, but you will see it in textbooks. When you see this, what they're talking about is this quantity. When we were talking about Fubini's theorem, we said that the change in area was delta xi times delta yi. That's because of the way we carved the region up. And the reason that we carved it up that way is in Cartesian coordinates, this kind of shape is the easiest kind of shape in the world to calculate areas of. This is eventually where the dx dy or dy dx came from in Fubini's theorem. What if you go back and think about our parallelogram? I'm going to think of the x-coordinate as being between A and B, and the y-coordinate as being between beta x and alpha x. The regular Cartesian version of Fubini's theorem looks like this, and a perfectly reasonable question is, what does it look like if I use coordinates alpha and beta instead of x and y? So I'm going to describe that region using these other coordinates. Just for convenience, I'll assume that it's the alpha that has bounds that are actual numbers. So alpha 1 and alpha 2 are constants. The alpha coordinate will be allowed to vary between them. Beta is going to vary between two functions of alpha. So if alpha were x and beta was y, we would be talking about the same kind of situation we discussed in Fubini's theorem. So the region that I'm going to think about now, alpha can be anything from the number alpha 1 out to the number alpha 2, and it's going to be bounded on the other two sides by beta being a function of alpha, u of alpha here, and v of alpha here. I want to think about chopping this kind of region up into small pieces, but since I'm not doing Cartesian coordinates, I don't want to split them up into little rectangles. I want to split them up instead of having pieces where x is a constant or y is a constant. I want to do the analogous thing in our new coordinates. I want to have sides where alpha is constant and beta is constant. I'm going to chop my region up into many, many tiny chunks, the vast majority of which look like this. To do an integral, I'm going to evaluate my function at a spot within this subinterval. It has x and y coordinates, but it also has alpha and beta coordinates. I want to evaluate my function. I want to multiply by the amount of area that I have here. I want to add up all such things, and I want to take the limit as the size of the chunks tends to 0, as we've done before. So I'm being very talky inside the parentheses here. The contribution to the integral is going to be f evaluated at a point whose x coordinates are xi, yi, and in the new coordinates alpha I, beta I, I'm taking a point and evaluating the function there. The point has more than one description though. I'm going to multiply by the area of chunk number I, which if I were doing Cartesian coordinates would be delta x delta y or delta y delta x, but we've seen that's not what's going to happen generally speaking. In the new coordinate system, the area is going to be this incredibly ugly notation, delta alpha delta beta, or incredibly ugly notation, delta beta delta alpha. Fubini's theorem in these new coordinates for nice regions R is going to be the integral from constant alpha 1 to constant alpha 2 with respect to alpha of the integral from v of alpha to u of alpha of, and now I have to be careful. In its usual formulation, f will be given in terms of x and y, but x and y are supposed to be functions of alpha and beta. So if I want to be careful about this, I'll write f of x of alpha and beta, comma, y of alpha and beta. Delta alpha delta beta can't be the area, so I have to include that ugly factor. That wasn't there in the Cartesian case, but it will be there in all other coordinate systems. So finally, we're starting to get somewhere now. Let's think about Cartesian coordinates xy versus polar coordinates r theta. X is r times cosine theta, y is r times sine theta. R squared is x squared plus y squared, and tangent of theta is y over x. You'll remember from trigonometry, we usually leave these formulas as is because sometimes it's convenient to take the r to be negative. In what follows, we will not take the r to be negative, which means we would go on and say r is square root of x squared plus y squared. That means if I'm not in the correct quadrants, I may have to do inverse tan of y over x. At times, it will be necessary to add 180 degrees with this. The area of a chunk in this picture cannot be delta r delta theta or delta theta delta r. The theta is in radians, which you'll remember really are dimensionless units. So the dimension of delta r delta theta is the dimension of length, not area. So this can't be the right thing to do when we do an integral. If that didn't convince you, think of having a delta r equal one piece and another delta r equal one piece further out. Have the angular size be pi over 6 on both of them. Obviously, this area is a lot bigger than this area, even though for both of those chunks, delta r and delta theta are the same. So there has to be more to it than just delta r delta theta. What's missing is the ugly piece of notation. I've got to write in the derivatives of x and y with respect to, previously I was calling them alpha and beta in general, but now we'll get specific. The new coordinates are r and theta. So I'm going to have to write down the partial of x with respect to r, partial of y with respect to r, partial of x with respect to theta, partial of y with respect to theta, take the determinant of that, and then take the absolute value of it. Partial of x with respect to r is cosine theta. Partial of y with respect to r is sine theta. Partial of x with respect to theta is negative r sine theta. And partial of y with respect to theta is r times cosine theta. I have to do the determinant now and take its absolute value. So if you multiply everything out, as we do with determinants, and to be careful about plus and minus signs, this term is cosine theta times r times cosine theta, r cosine squared theta, minus something times the negative of something else. Minus minus is plus, r times sine theta times sine theta, and then a miracle happens. Inside the absolute value, split the r off. Cosine squared of theta plus sine squared of theta is 1. So really, I should, if I wanted to be picky about it, write down an extra factor of absolute value of r. But I said I was going to make the choice that the r was always non-negative. If I make that choice, polar coordinate, blah, blah, blah. If I make that choice, that very ugly piece of notation simplifies down to r. This is the shape that corresponds to a rectangle. Using polar coordinates instead of Cartesian, I'll have some theta value. Theta equals theta 1. I'll have some other theta value. Theta equals theta 2. This part is the arc of a circle, so I'll have r equals r1 for this part, and r equals r2 For that part, this is going to be reach in capital R. Capital R is described this way. R is less than or equal to R2, but bigger than or equal to R1, and theta is bigger than or equal to theta 1 and smaller than or equal to theta 2. Some people call this a polar rectangle. In view of what we've said, if I want to do the double integral over a region of this type of a function f, which depends on x and y, integrated with respect to area, in polar coordinates, this is as easy to do as integrating over a rectangle is in Cartesian. I'll put the theta on the outside. Integral theta 1 to theta 2 d theta, integral from r1 to r2 dr. The thing I'm integrating is f evaluated at x and y. X is r cosine theta, y is r sine theta, and I've almost written the correct iterated integral down, but dr d theta is not dA because of what we talked about previously. I have to have that ugly factor, but the factor isn't actually that ugly for polar. It's just r. So whatever function f is of x and y, express the x in it by r cosine theta, express the y by r sine theta. Don't forget to put that extra factor of r in, and now this integral is easy to do. This has been the development of the two-dimensional version of this work. We will move up to 3 dimensions at some point, which is why I wanted to mention the parallelepipeds. This is all I wanted to say in this discussion. In our next meeting, we will work some actual problems like this. We will do double integrals in polar coordinates. In the meantime, I hope everyone's having a good day. I'll talk to you again soon.